Today we're going to talk on the Ediacaran, which is one of the periods of geological time, extends for 94 million years or so. And if you think it sort of straddles about 600 million years ago. Now, might be a bit vague to start on this subject, but Ediacaran is very important to us in South Australia because it's a geological period that's defined in South Australia, if you're not aware of that. And it's based on the earliest animal life yet recorded in fossils. There's some sort of complex metazoan, they're clearly animal, but we can't classify most of the forms, or really any of the forms but one, into what we call modern animal phyla. Now, Ediacaran, as I say, it extends for 94 million years, which is longer really than things like the Jurassic and Cretaceous. Offhand are more like 50 million years, and the entire Cenozoic era is only about 60 million years. So the Ediacaran is quite a large chunk of time, and it's defined in South Australia in Flinders Ranges, particularly along the Bratchner Creek geological section, which is defined as a geological trail for those who drive along it. Now, I'm just going to introduce this with a discussion of supercontinents, or megacontinents even. Now, supercontinent, to my definition, would be something like Gondwana, with which we're familiar. A couple of 100 million years ago, southern continents were grouped together in a fashion like this shown on the diagram here. We were actually moving over the South Pole at that time, in that we have evidence of ice age at Hallett Cove, where I was there on Saturday, actually. Enjoyed a very sunny, beautiful day. Friday, beautiful morning. The continents were grouped together. Of course, in the last 100 million years, they've separated to the extent that Antarctica and Australia are 3,000 to 4,000 kilometres apart. Same with India, which moved north and created a new ocean to the south, the Indian Ocean. Africa and South America are also separated, and there's a tenuous connection still between South America and Antarctica. Well, most people would say no connection south of Cape Horn. I won't go into the details. Yes?
Excuse me, Bob, does this mean that South America and Africa were actually that close to each other?
Oh, absolutely.
Yeah. Oh,
yes.
Yeah.
Yes, absolutely. Quite co-joined. And in the continent of Pangaea at that time, that's a megacontinent of Pangaea, which includes the northern continents. These two were a bit rotated and jammed against North America, so that you could probably step off from Venezuela to Louisiana or the mouth of Mississippi, and you could probably step off something like Libya to near or not quite as far north of New York, to Atlanta or somewhere like that in Georgia. Unbelievable that both those continents then rotated away and separated in the last 100 million years or so. Anyway, to go on from that, we're talking about this. I wanted to talk about the supercontinent cycles, and we've Gondwana and the overall megacontinent Pangaea, which existed roughly from 500 to 100 million years ago, before all the separate parts broke away. And South African geologist J. Tuzo Wilson actually, you could mute yourselves if you would, because anything abnormal will come through on the recording. If you don't want your faces on the recording, you can also close your videos temporarily and come back later. But anyway, the Wilson cycle, he realized when he looked at particularly the North Atlantic, showed that these megacontinents not only separated, but they'd been together and separated previously, that there was a sort of cycle of continent breakup, formation of a new ocean, and ultimately separation of the continents. And then the tendency for continents to come back together again and form a new super or megacontinent. And this whole sequence of cycles would repeat. So that in fact, there have been 3 Atlantic oceans, if you use the word Atlantic in inverted commas. Now, this is usually referred to in geological literature as the breakup and rejoining of Laurentia, which is the Northern American continent, USA and Canada, and Baltica. These were Baltica and other sections like Siberia and Kazakhstan are usually referred to as Laurussia when they are joined with North America. There's that Laurentia and Russia. So North America and all of Europe, Northern Europe, joined in one supercontinent. And there have been really 3 Atlantic oceans. They've all got names and they're all pretty well studied, particularly in the obviously North Atlantic between Newfoundland and the British Isles. Now, okay, we're conversant with Pangaea, going back to about 500 million years when it first started to come together. But prior to that, there appears to have been another major megacontinent on Earth, which has been named Rodinia from Russia, homeland, I think it means, or something like that. And its breakup occurred in around 700 million years ago. And this is just prior to the Ediacaran. In fact, South Australia records a portion of the breakup, 1/2 of the breakup of the original supercontinent Rodinia. The other portion was a section of South China and Laurentia, the northern part of America, so that these separated about 700 million years ago. And the process of separation and coming together is a bit like the ice sheets, which I keep referring to. You can picture down in the bottom, North America, say, and then East Antarctica attached to Australia in the middle, South China poked in between. And these are just showing a section of glaciated, pack ice, actually in the North Atlantic. And look at the distribution of continents. This is more or less as they were in the supercontinent Rodinia, with the new oceans forming at the time of breakup, represented by these darker leads between the ice flows. And in future, you'll see how similar these slabs of pack ice are to the continents. They've got sections of older rocks or older ice flows, all broken up but joined together. And that's the way continents seem to have acted. And probably the whole process is very similar in that warm ocean currents are welling up here and causing the blocks to separate with the new leads, ultimately separating them so that they're just floating ice surrounded by ocean. That's just how the process megacontinents or supercontinents break up. And here's another picture from a paper in which the authors were arguing about a super plume of heat that had come up from the Earth's core, focusing essentially on South China, Australia and East Antarctica, which caused a cracking, you might say, a triple point represented by the red lines, which are the spreading centres of new oceans. And that accounts for the separation of Rodinia about 700 million years ago. It happens that at that time, the Earth had been going through a series of ice ages, which lasted 50 to 100 million years, it would seem. And it's thought that the whole globe was glaciated, that it was a snowball Earth, they call it. And this is the modern theory for explanation of ice age effectively on every continent as we know them of this age of about 700 to 600 million years. There's two very clear ice ages, possibly a third, a bit younger. And in that case, the younger one, if it is well established, will be found in the Ediacaran, which is the period defined in Australia. Moving on from that diagram, I won't go into the details of that mega plume shown with the orange dots. Of course, volcanic centres of about this age, about the somewhere between 840. Oh, my internet connection is unstable. My goodness, I hope it doesn't cut off. Do you hear me?
Yes.
Can you hear me?
Yes.
Can you all hear me?
Yes.
Steely, do you hear me? Right, good.
It's
Right, so here's
speaking, Bob.
another picture of the fragmentation, yes? Of fragmentation of Rodinia, 750 to 600 million years ago. And you can see Australia, for a long time, we've travelled with East Antarctica, possibly for as long as 1.5 billion years. And the history of India and East Antarctica is a little less obvious, possibly also a very, very long period, over 1 billion years. But about 3/4 billion years ago, things started to crack up from those continents having been apparently all together. And they had separated in this way about the time of the ice ages 700 million years ago. However, and all the continents appear to have been glaciated at that time. However, the pinker areas on these are areas that have been formed subsequent to that period. So all of Eastern Australia effectively is younger than that 600 million years, and sections of the transantarctic mountains of East Antarctica, West Antarctica, the real peninsula out to South America, is all younger too, but it's not shown on this diagram. It's actually been developed as new continental material. The whole of the Western Laurentia and Eastern Laurentia. So the Rocky Mountains and the Appalachian Mountains of the East Coast, which at that time also corresponded to the mountains of Baltica and along the coasts of Norway and Greenland, but corresponded in age. It is along that trend that the oceans have opened several times. You notice here there's a different name, the Iapetus Ocean, the son of Atlantis. Or is it the father of Atlantis, perhaps? I beg your pardon. And there's yet another one named after the uncle of Atlantis, which are the three ocean names applied to effectively what is the Atlantic Ocean today. But the continents all come together again in that region twice in this interval of 750 million years. Just one more to make, to emphasise it, the breakup of Rodinia occurred around the time of the 700 million year ice age. And Australia was more or less equatorial, at least in the latter part of that. And so it's pretty amazing that we've got a record of glaciation shown by those white triangles that extends right across the country from western northwest Tasmania, King Island, through the Flinders Ranges into the Amadeus Basin near Alice Springs, right out towards, I'm trying to say Mount Isa region, and also in far north Western Australia and in the Kimberley province too. So South China has very, very similar units of glaciation, two, perhaps a third in number, as we have apparently that third one. The northernmost one in the Kimberleys appears to be younger and Ediacaran in age. And all along the west coast of Laurentia, even in the Amazonian region, the Congo, Namibia and elsewhere, the ice ages in Scandinavia and in Greenland and Scotland and the Scottish Isles, I should say, are all about this age and apparently related to a global ice ball. So about this time too, there were big jumps in evolution, and I won't go into this in detail, but the cell form was very, very primitive early on. The various green algae and simple forms that we know today, just single cells, and initially they had no nucleus, the prokaryotes, such as bacteria, but then somehow they captured another cell which became a permanent nucleus, apparently, and that gave you the eukaryotids, and although they existed for quite a long time, they blossomed after these ice ages, and with the global warming that came in during the Ediacaran, just under 600 million years ago, you got significant development of these forms with a cellular nucleus, and they're the ones that led to future animal life. The DNA in those was linear, and that probably led to the possibility of cells repeating each other and crossing over to give some form of what we call sexual evolution. Oh, we're going to talk really about Wilpena region, the Flinders Ranges, or Ekara National Park, dear to our hearts and close to home, and that's the type area for the definition of this big long interval, the Ediacaran. You probably get the best view of it from some of the lookouts that give you the view of the ranges across to Wilpena Pound. This is one that you strike 20 or so kilometres north of Wilpena, going up to Blinman on the Bitumen Road, Huck's Lookout, and on the skyline is the big spoon, structural spoon of the Wilpena Pound. But all the sequence from the point at which you're standing to the far distance is effectively dipping away from us at an angle like 30 degrees or so. So the strata are getting progressively younger as we go to the southwest or into the distance here. And much of this succession is what we'd call the Wilpena group. And Wilpena group has been defined effectively as the Ediacaran period. So all those rocks from at least the shadow in the middle distance right out to the skyline represents the strata deposited during the 94 million years of the Ediacaran period. And this is at Huck's Lookout. There's a geological section, and effectively we're on the right-hand side of that, looking across the succession where I've written Ediacaran period. Probably when the sign went up, we didn't have the classification of a period, which was done in 2004 as the first definition of a period in the geological table for over 100 years. It's the only one from the Southern Hemisphere. All the others, like Cretaceous and so forth, are named from major features of Europe. And I won't read everything on that, but they say sediments between about 1,000 and 500 million years. Well, there's nothing as old as 1,000 million years there. The oldest probably 800 million years if you dated some of the rocks in the Oropenina and Blinman domes. And that's when the continents started to break up and the whole region was a rift valley, later invaded by the sea. There were volcanoes in that rift valley, much like the East African rift today, which is precursor of forming a new ocean which separate Tanzania, etc., or Tanzania, if you prefer that. The rocks are usually mapped first and named, and hence we have names like Pound subgroup for the major peaks that form the saucer of Wilpena Pound. And we have ABC range quartzite as an outstanding, or sandstone as an outstanding ridge in between that. And Brachner and Bunyaroo formations are red-brown siltstones, very characteristic to the successions that you look at if you make the drive from Bunyaroo and Brachner gorges. So, as I say, it's 94 million years duration, straddling about 600 million years ago. And before Ediacaran, life was simply slime and single cells or mats, strings of cells, etc. But then these cells with nuclei took over after the glaciations of about 700 million years. So there was a glaciation somewhere around the perhaps the 630 million years or so, and it would be classified as Ediacaran. And particularly after that period, we see an increase in particular type of organism that had or chitinous type of shell, only a single-celled organism though. Now, stromatolites had existed for 3 billion years, and those and their relatives, the green algae, etc., had really developed our atmosphere. Certainly by 2.5 million years ago, they'd oxidized the oceans and given us our iron formations and so on. But no organisms with hard parts really existed until, well, these acritarchs blossomed just about the time the first of the major ice ages was over. And in South Australia, we had a very big impact by an extraterrestrial body out in the Gawler Ranges about 580 million years ago. And it seems like that there was quite a flourish of these small, still single-celled organisms immediately after that. So the time of the Ediacaran fauna, or the fossils that are known as animals, it's only the very upper part of the Ediacaran period. Possibly we got a bit ambitious in having it defined way back to 635 million years or so. And that was based on more on the completeness of the geology of that Wilpena group. It made it quite satisfactory to define that as a type succession, you might say, for a very long period. When you think about it, 94 million years, sufficient time for all the mammals to evolve from the very earliest ancestors back 150 million years ago, or 100 million years ago. Now, when we come up to the Wilpena National Park, Rawnsley Park is one of the first notable locations, I suppose, other than Aqaba and or beyond Hawker and going north towards Wilpena. And the Rawnsley Bluff gives its name to the most outstanding or boldest outcropping unit of the Pound group, and the whole face is effectively the Pound group here. Even the lower slopes are one unit of the Pound group, whereas these formations, and remember the Rawnsley Quartzite embraces the Chase member and the Ediacaran member, as well as the rest of the unnamed section of Rawnsley at the top. Reading that and driving to the tourist centres of Rawnsley Park and Wilpena Chalet in the Flinders Ranges, the most outstanding view is Rawnsley Bluff on the southern tip of Wilpena Pound. The structure of the pound is like a spoon formed by the Rawnsley Quartzite. It's 12 or 15 kilometres long, of course, and it's above softer beds of the Wilpena group. So it's only natural erosion which has resulted in the Pound structure as a result of this spoon-like or synformal basin structure. And there's a handle to the spoon that runs all the way up the Flinders Ranges to Parachilna, which is itself a type syncline. Now, those rock relationships that I've mentioned, the pound subgroup, it comprises the softer and red-coloured Bonney Sandstone at the base, named from Mount Bonney, or the Bonney Peak at the northern section of the drive along past Wilpena Pound. And this is largely non-marine and tidal, as the Rawnsley Quartzite above it is much more marine, and although it's also sand, and there's a range of environments recognised in that upper hard unit, which include deltas and intertidal zones, fully marine variants, canyons offshore and this sort of thing. And many of the Ediacara fossils appear to be preserved below wave base, below storm wave base. That's probably 100 metres down in depth of water. And they're occurred in trenches, small canyons, in mass flow sand bodies that are the result of underground sea slips, you might say, underwater sea slips. So the sand has formed a turbulent body that has slipped down, taken with it many of the living forms and redeposited them in deeper water. Now, geologists like to look at stratigraphic columns which illustrate the sequence of strata. Redder ones are shown here in red, such as the Bonney Sandstone in the middle, or the Bunyaroo Formation underneath it. The Brachner lower down again is also quite reddish. They're more silty than the yellows, or the pale yellowy green colour. Rawnsley Quartzite in the middle with its Ediacara member outlined in red. And you see a number of fossil forms illustrated beside that. This gives a quick view to the geologist of what the strata are like, which of them have fossils, and what the fossils are actually like. Higher up in the succession, you see things like a vase or a cone. That's in the main limestones of Brachner Gorge, which are the big dark bluffs that you drive through in the western part of the gorge. And it has abundant fossils called Archaeocyathra, which are like a double ice cream cone perforated by pores. We don't actually know the fossil form that lived in these, although they might well have been quite simple. They were probably a bit like a sponge, but they formed enormous reef structures which extend effectively across the world. They were periodic appearance, of course, not necessarily a huge barrier reef all over the world, but shallow water areas in these limey rich seas produce reef mounds that are sometimes quite thick. There's one in the Flinders Ranges about 1 kilometre thick, extends for 3 or 4 kilometres along the strike. So it was a huge mound which persisted for tens of millions of years, I believe. And then finally, the whole succession reverts to red sandstones and red siltstones and shales of the Lake Frome group. At the bottom, we find cryogenian. That's a new term that's not actually yet defined, but it will be defined, and we're rather hopeful it might be defined again in South Australia, possibly out near Lee Creek, where there's a very good succession of the older glacial formations, such as the Elatina Formation, which is the youngest of the 2 major ones. This succession doesn't include more than half of the older rocks, which go back from 630 million years, shown on the left-hand side as the base of Ediacaran. They go back to 820 million years, particularly in the areas around Arkaroola and Maree in the Willowran Ranges. So that's the way that geologists tend to look at a stratigraphic column. And of course, this is all put together by looking at the rocks, recording them in detail. And here's someone looking at a rather fascinating repetition of little layers. Anyway, I was saying that twice a month, you effectively don't get much of a tide at all, whereas in the alternating period, when the sun and the moon are pulling together, you get what's called the spring tide, or quite a strong tidal development. And that can be picked up in the rocks by alternations of sand and mud quite frequently. And I won't go into extreme detail with this, but you can imagine when you see this sort of alternation in the rocks, you think, ooh, I wonder if that's tide. And people have worked on this in great detail, and you can find mud, you can calculate all sorts of things, how many tides per day. And in fact, in one area in South Australia, they've been able to calculate the number of days in the year from this as around 400, would you believe? So that in those times, Earth was spinning faster, the moon was also closer, so the tides were more prominent than today. Suffice to say, we see that phenomenon in the sediments, and this is quite evident in the Ediacaran succession, or the Wilpena group of the central Flinders Ranges. We see this patterning, which tells us that that was, or we believe to be, tidal. And even down to very fine scale, in what is possibly deeper water, we see these fine laminations here, only centimetres or so in width. Each little black square on those scales is 1 centimetre, so that you can perhaps see the banding, and again, even finer in this particular rock. And we put that down to the effect of tide and the depth of water in which the tides are being represented. Suffice to say, they're present in the Bonney Sandstone, which is the lower unit here, even though I have already said that a lot of it is non-tidal or non-marine. And it gets more marine, it seems, as we go up into the Chase member and the Ediacaran member, which are quite outstanding when you look south at the range from, perhaps you've done the Ratchner Geological Trail and stopped on one of the big scree slopes, perhaps to view ring-tailed wallabies. Well, if you turn around at right angles and look south, this is the view from there. And main Rawnsley Quartzite, this is all Rawnsley Quartzite above the Bonney Sandstone, but the members of it are the Chase member and the Ediacaran member, which actually has 3 units that we'd recognise as major influences of sea level, even within a matter of 15 or 20 metres. There are 3 zones that coursen upwards, suggesting the water was shallowing. Then all of a sudden it got deeper again. And that's a phenomenon known throughout the geological column as big fluctuations in sea levels, probably resulting from the amount of ice in the polar regions. There's no evidence at this late period of ice on Earth, but there may well be proved in some way. I've just outlined there the upward coarsening units as we see them, but there's a fault down the gorge itself, particularly as you enter it from the east, and that disrupts the succession, duplicates it, but it also allows you to see the Ediacaran fossils in one area, particularly in the centre of this diagram or picture. So there's a board along the track, somebody standing in the bottom right-hand corner there holding a bit of a notebook, perhaps looking across to see where the illustrations of fossils would be. And there is a notice board indicating that if you go across to perhaps the right-hand the small trees in the central part of the picture, it is possible to find these Ediacara fauna. Another view of that, the fault disrupting the succession there, and you can see the scale of that fault. It's probably 500 or 600 metres in throw or in movement. Because a geologist working there laboriously tries to unravel the faults and get the correct succession, and he'll record information rather like the left-hand side of this diagram. This is not directly done in the field in this case, but try and interpret in each case whether it's the front of a delta, pro-delta, or the tidal section of a delta. Perhaps it's gone non-marine into an alluvial plain, as I move up towards the middle part of the diagram. And again, flooded by intertidal sand flats, getting deeper in the pro-delta succession, and somewhere around the storm wave base at the top there, with the more shaly strata and perhaps a lot of indications of preservation of fine material, fine details on the surface of the bedding, and then going back again into wave zones and intertidal sections. So all those interpretations are done from a lot of structures in the sediment, and some regions of it are done in more detail for particular reasons. Either a student has worked on it, or we are interested because of the occurrence of fossils. And obviously the fossils also get recorded on those successions. Just looking back at that more general one, we're really only showing interest in the pound subgroup in the areas illustrated by that red block. Actually, pound doesn't technically go into the Cambrian, so that this drawing of this diagram has shown the yellow pound extending up into the lower section of the Cambrian. That's not really very valid. It should be within that red rectangle. This is a stratigraphic column or a table, and showing the strata, or some of the strata exposed along that Brachner geological trail. It highlights in that red zone the position of the pound group, where the Ediacaran fauna seems to be preserved in ravines or canyon-like erosional features. Maybe they're only huge tidal scours, but they have dimensions of up to 100 or 2 meters. Now, in one of the finer successions, here's a group of geologists lazily looking at fossils, although Jim Gayling there with a specimen in his hand has done more for the work on Ediacara than any other geologist, perhaps with the exception of an American woman who comes out, I think, from California every year for 18 years. I think she's come out to work at Nilpena Station on the Ediacara fauna, and I'll go on to that shortly. But the fossils, they're actually found on the underside of the strata, which are dipping at about 30 degrees here. And that hand is pointing at where the fossils are likely to be found. You really need exposure of the base of beds in order to identify them, in that they're death masks or impressions when the overlying bed of sand or silt lower bedding plane, but only their remnants were preserved, only their impressions were preserved. And if you turn the slabs over, here's one of them, obviously 15 centimetres or so long, and silly putties being used to get an impression which would have been the correct fossil form, of course, since it's preserved as a dead mask by the overlying unit. You need to turn this rock over and create an impression to see what the animal was actually like. This is an unusual form called Dickinsonia, after the director of mines at that time, who was being encouraged to allow a fair bit of work to go on around the Ediacaran fossils. They were discovered by Reg Sprigg, a well-known geologist who worked down here in the southeast as one of his first jobs, and he obviously named this one after his director. It was 1945 when he was working with the mines department, lead zinc exploration out near Ediacara, which is northwest of Parachilna, and he identified the fossils in the sandstone, although they were drilling overlying limestones for lead and zinc. One other impression here in the bottom left, you can see one that looks a bit like a centipede, and that's named for Reg Sprigg himself. That's Rena, and emblem fossil, one of the very few forms that looks like a modern genus. Now, here it is in the original rock, so that's the death marks, or the impression of it from the top overlying sediment. And if we put the silly putty on that and pulled it off, we'd get a better impression of what the actual animal looked like. It's a centimetric scale, so it's about 5 centimeters long, and it clearly had a central axis, a head and body and tail. Well, when I say tail, there's nothing very obvious there, but it looks a bit like, and that's one of the few late to modern phyla. So Sprigina is a state fossil of South Australia, named after the discoverer, Reg Sprigg, and it's the only Ediacaran fossil to have a defined head and body. There were no limbs, or and they say an elongate crescent shape. I think it was an elongate shape rather than a crescent. However, that's Sprigina. And this again is Dickinsonia, again on the rock face. So it's just an impression of the top of the animal. And I think we showed that one. I don't think I'm going backwards. That's again the view of the uninterrupted succession, whereas we would be looking at the Ediacaran member over to the right, in fact, to the right of this particular picture, because a fault runs up parallel to that red line, which is defining the Rawnsley Quartzite, but running effectively from the tree back to the southwest, and that fault disrupts and brings the Ediacaran member a little bit closer, a little bit further down section, down meaning easterly. And Bratchen Gorge is the easiest accessed exposure of the Wilpena Pound sandstones, because you can drive right up through them. And so that's where most people would get their introduction to this famous faunal assemblage. And it's labelled along the track. It's about 40 to 550 million years old. The base of the overlying Cambrian is 541. So the suggestion here is that the pound might just overlap the Cambrian boundary. To carry on this discussion, we go further north to Parachilna, and we have the Ediacaran capital of the world, where fossils rock. Many have just buzzed past the little township of Parachilna, where there's only about 7 or 8 permanent residents, maybe even less now that it's effectively taken over by the family from Nilpena Station, the Fargers. But they have a bit of an artistic presentation of things like Dickinsonia as a sculpture, and they also have illustrations of the fossils locked by chain onto various viewing points around their courtyard. And quite good specimens of Dickinsonia, for example. Again, we can see that this would be the order of 6 or 7 centimeters long, but they do grow up to, I think, 1/2 meter, and even perhaps it's larger. They prove that they were capable of movement on the substratum. They could have presumably go along like an effective mop and collect all the fine algae and planktonic, or not planktonic necessarily, sorry, bottom-dwelling organisms for their food. And they leave a little trail quite frequently. In good situations, we'll leave a trail where it can be seen they were capable of movement. Maybe a rippling effect allowed their progress across loose sand. And the other one I've just shown is the most abundant, largest of the Ediacaran fossils. Well, there's a whole range of different forms. Some are probably growing like branch tree or shrubs, and we don't know the size of many of those. We only get fragments of them. Many were attached to the bottom, but this one was clearly free living. It had no mouth though, and thought to have digested algae by sliding across the surface of the ancient sea floor. Now, Jim Gayling in particular has done a lot of study of the various environments, and where originally Reg Sprigg particularly and others people considered that these things were preserved on beaches. He now has demonstrated that most of the occurrences actually are in ravines or fairly large scale, small canyons, you might say, and frequently in mass flow sands. That means they've come down in great slumps or subsea slips and very rolled about and contorted, and it's only the unusual ones that have been preserved where they perhaps survived to work on the seafloor and digest a bit of the algae and then got covered by the next sheet flow sand. So a great deal of study's gone on to the nature of the sediments and what they represent in terms of offshore sand flows. The here is not very prepossessing. That's Nilpena Station, where we're in the act, or people are in the act of making a heritage region. We look into Wilpena Pound right in the middle distance. You can see the spoon form of the basin, or the syncline as geologists would refer to it, of the Wilpena group. And the middle distance, Nilpena Station. The foreground, you can see little slabs lying around on the surface. Now, they're all, because of the relatively shallow dip, it's only a few degrees, perhaps 10 degrees dip in this region. All those are facing up, so there are no fossils on their surfaces. It's only where they've been overturned that you would find impressions of the death masks of the original fossils. Little quarries there have been constructed to get a better look at the style of sediment. Excavated individual beds very carefully and reinstated them a short distance away. They've laid them out as floors of overturned beds. So they're pieced together as jigsaws. And that represents one stratum, or one little layer of the seafloor that's been quarried and laboriously laid out platforms that they've made lying on the surface of the hill. In the distance, we're looking at reddish coloured Bonney Sandstone, which underlies the Ediacaran member, and slight dip to the east because we're looking westerly essentially. And there's also a modest canyon cut into that Bonney Sandstone, running about from where the person in blue stands, well, where the head of that person in blue stands. Slight change in colour, and a line runs out to the left-hand side. And that line that I referred to is the green contact running across. And of course, it's only 10-degree dip to the northeast here, so that even over a couple of kilometres, you haven't gone more than, well, at most a 200-metre thick canyon fill of the Ediacaran member shown in green. That's the incision into the Bonney Sandstone. You can see illustrations of various forms there.
Yep.
Many of the things that used to be considered to be jellyfish, is that Aspidella. These are probably fission discs for sort of arborescent type animal, which is shown in the second one there, Chanodiscus. That's actually named from somewhere near Robin Hood's forest, the Charnia forest anyway, in England. And you get bundles of fibres, which may be, this is on the top right, which may be portions of a plant-like structure, various other forms, even a different style of Dickinsonia. And at the bottom left, a trigonal phenomenon showing 3 radial arms. And of course, modern animals don't have trigonal symmetry. Anyway, There's a whole variety of these things. Hopefully that changed too and gives you a look at a rugose surfaced one, other probable fixation things, one with a little anchor within a lozenge, Parvancorina, and a better one perhaps of Sprigina, illustrated on the central right-hand side. So some of those are quite large. That I think, oh, I can just see fingers in the right-hand side below our pictures. One doesn't know whether that was a fixation device or a flat jellyfish-type structure. Some may be that, but they've gone away from that idea of interpretation these days. Again, one of the unusual, maybe a soft-bodied animal. I think that one has some indications of movement on the surface, so it may not have been a fixation feature. Many of these are on rippled surfaces, and we have to remember this is actually the upside down impression of ripples. I think it might be Jim's finger, maybe mine, I'm not sure, pointing out what was the top of a ripple, and on it would be, I think was preserved a Dickinsonia, very nicely preserved on the top of a ripple. Various other little features that we have no idea what their relationship is, only a centimetre in size. And possibly a small fixation body, other fractured ones, a corona of material there that extends for about 15 centimetres around a central smooth zone. Has to go into anything that looks like that to try and work out whether there are different life forms or exactly what the geometry of this fossil was. And there again is another Dickinsonia, which they've pieced together on both sides of the stratum. In fact, they can relate that one, I believe, to the top of the bed that was extracted from underneath it. So in the Brachner geological succession, we see a man fossil over there at the base of the Parachilna Formation, which comes in immediately above the Rawnsley Quartzite of the Wilpena group. So it's effectively the start of Cambrian, and it's laced with worm burrows, with vertical burrows or U-shaped burrows of Diplocraterian, we'd call it. Absolutely a pipe rock. Every piece of sediment's been worked over in the alimentary tract of a worm, and these are modern forms, and they come in quite suddenly with this Parachilna Formation dating at about 540 million years. It's not 550 million years. It would be more like 540 or 541. So that sign is older. This is near the Teamsters Park area. It's worth walking up the little gorge or little creek. Effectively, the man is looking at. He's looking at the top of the Pound subgroup or group, and behind him, where his bottom is, you're into the Parachilna Formation, which is the Wormborough Sandstone. So we then move into the Cambrian explosion of life, and within a matter of a few million years, almost all the modern phyla appear in the geological record. Alimentary tract have made it possible to work through the subsurface of the sediments, which in fact destroys a lot of the features, like that tidal banding gets destroyed by marine animals by the time the Cambrian came round 541 million years ago. You do, however, get marine animals with hard parts, very shelly fossils, and all the modern phyla, sponges, corals, mollusks and gastropods, arthropods in the form of trilobites, and also predators on these, so that there became evolutionary trends for protection from predators and also specialization of predators, which we can discuss another time. But of course, there's still no record of life on land in the Cambrian period. I think we'll close it today. Bye now. Yep, cheery now.